Good morning, everyone. My name is Zavia Ashraf from Information Technology, holding roll number 24951A12C8, course Data Structures, course code ACSD08. Today, I'll be presenting on cutting-edge topic in artificial intelligence and computer vision, deep residual split-directed graph convolutional neural networks for action recognition. It sounds complex, but at its heart, it's about how we can teach machines to understand human movements in a way that's accurate, efficient, and intelligent. This has major applications in security, robotics, healthcare, and sports analytics. Let's dive in. Introduction to Human Action Recognition. HAR. What is HAR? Human Action Recognition, or HAR, is the task of teaching computers to identify that people are moving from video data. For example, recognizing if someone is walking, running, throwing a ball, or waving. Why it is important? HAR has huge real-world application: surveillance, detecting suspicious activities automatically; human-computer interaction, gesture control system; AR/VR, robotics, robots that understand human behavior and assist intelligently; sports analytics, track and analyze player movements for performance. Traditional video-based method faces issues like varying viewpoints, occlusion, parts of body hidden, light changes. That's why researchers move to skeleton-based HAR, where a skeleton-based is extracted and analyzed instead of raw video pixels. From skeletons to graph, the rise of graph convolution system. The human skeleton can be neutrally represented as a graph. Nodes can be represented as joints, and edges can be represented as bones connecting them. Using graph convolutional systems (GCNs), we can capture both spatial relationships, how joints connect in one frame, and temporal relationships, how they move across frames. Early GNCs only linked identical across frames, but this misses richer interactions like wrist-elbow coordination in throwing. This is where advanced models step in. Early applications of GCNs in action recognition primarily focused on connecting identical joints across consecutive frames. While this approach showed a promise, it often overlooked the more complex and nonchalant interaction between different joints that are critical for defining actions. For instance, coordination between a hand and an elbow during throwing motion is more indicated than an individual joint trajectories. Addressing this limitation has been a key area of research, pushing the boundaries of GCN, graph convolutional networks, to capture the richness and descriptive features. Directed diffusion graphs, modeling physical dependency and synchronization. Directed diffusion graph (DDGCL). Unlike static or symmetric graphs, directed graphs add directional edge. Wrist depends on forearms. Arms depend on shoulders. So there is a direction. There is a flow of direct lines. This mirrors real biomechanics and allows information to flow more naturally across skeleton. They also include spatiotemporal synchronization encoder, aligns joint movements across times, capturing finer details like the difference between waving versus throwing. Second is split strategies. Skeleton split framework. Joints are divided into subsets before convolution. Spatial split. upper versus lower boundary, distance spell, connection spell, index spell. Why it is useful? Because actions often depend more on specific subsets. Example, kicking is legs matter more, while throwing a ball, arms matter more. On datasets like USC 101, the index spread strategy had 73.25% accuracy, beating older methods. Deep residual networks. Residual networks allow very deep model without vanishing gradients. 3D CNNs capture not just parietal data framework image but also time dimension. Combining ResNets plus CDCNNs and GCNs includes very powerful for HAR. Learns more both parietal and temporal patterns effectively. Hierarchically decompose GCNs. Hierarchically composed GCNs process skeletons at multiple levels, local as well as global. With attention mechanically, with attention mechanisms, the net the network dynamically focuses on relevant joints. Examples: punching, arms and shoulders get more weight, walking, hips and legs get more weight. This adaptive focus leads to state-of-the-art results on NPU and RGDP datasets. Deep residual networks and 3D CNNs. Uh, Complementing this, 3D CNNs are specifically designed to process video data. Unlike 2D CNN that operate on individual frames, 3D CNNs apply convolutional filters both across spatial dimensions and as well as temporal dimensions. Hierarchically decomposed GCN, capturing long data dependency. Furthermore, uh, HDGCNs decompose the datasets of joints into hierarchical sets. This means they can simultaneously process interaction immediately between immediately adjacent joints and long data dependencies between more distant yet functionality related joints, hand and foot during dance moves. The multi-scale approach ensures that the model graphs the full complexity of human kinematics. Furthermore, HDPCNs often incorporate attention-guided hierarchy aggregation. This also allows the network to dynamically highlight and prioritize important joint interaction based on specific action while performed. For instance, during a punching action, the model might pay more attention to the arm and shoulder. Putting it all together, deep residual split directed GCN architecture. The accumulation of these innovation techniques results in powerful and robust architecture. The deep residual split directed graph convolutional neural network. This architecture harmonizes several edge cutting concepts to achieve superior performance and skeleton based action recognition, such as directed diffusion graphs, splitting partitioning, deep learning. These graphs are foundational, capturing the physical and temporal dependencies between joints and explicit directed edges. This ensures the information flowing kinematically sound pathways, leading to more accurate modeling of human. The synergy of these components allows the DSRD GCN to achieve superior accuracy, robustness on challenging bench, NTU RGB plus D, NTU RGB plus D120, and NWUCLA datasets, solidifying the position as leading approach in the field. Visualizing recognition and after directed split GCN. Let's visualize traditional GCN, which captures the moment but fragmented misses subtle relationships. And then we can uh, visualize deep research data GCN. which is smooth, synchronized representation accuracy distinguishes similar action. This is what makes difference between a robot that sort of understands you and one that perfectly recognizes your gesture. To wrap it up, GRSD GCNs represent a big leap in skeleton-based HR by combining directed graphs, split strategies, and residual learning. We achieve high accuracy and robustness. What are the future directions? Real-time deployment for surveillance for live HCL, multimodal fusion combining skeleton data with RGB depth audio, supervised learning, reducing redundancy and labeled data sets. In essence, action recognition is moving towards systems that don't just see humans but truly understand movements or content. Thank you.